All right, welcome back again, everybody. Today we're doing section 2.2. This is all about the graph of a function. So we're going to bring in some of that geometry to make functions make a little bit more sense, get some visualizations, which are pretty nice too. Let me pull up the slides, and here we go. Right. So section 2.2, here's a quick overview. Again, we're going to see the stitching together of algebra and geometry, BFFAE. We're going to talk about the vertical line test. You might remember that if you've seen this before. We're going to talk about how to get info about a function from its graph. One of the nice things about graphing a function is you can get information about the function itself that is easier to interpret when you have a visualization of it. We're going to talk about the very important idea of finding the zeros of a function. Then we're going to see some graphs of some important functions. This is one of those few times where I'm going to say you need to memorize these graphs. These graphs are absolutely essential. They show up forevermore. A lot of the graphs and functions that we see after this are just going to be transformations of those graphs. So these are ones you do have to memorize. Then we're going to talk about piecewise functions, which are basically functions where the rule changes depending on the input. We're going to talk about how to combine functions using the four basic operations. But to do that, we also need to step into a little bit of set theory, talk about intersections of sets so we can make sense of the domains of these compositions, or I'm sorry, of these combinations. And then in the end, we're going to talk about graphical arithmetic, which is essentially doing arithmetic using the visual graphs of these functions. That actually makes interpreting what the result of a combination of a function will look like much easier. And we're going to practice it during the activity as well, where we're going to do physical graphical arithmetic. Pretty fun. All right, so let's get started with this. We know what functions are, and we explored them as a very abstract concept, right? So we want to investigate the properties of these functions, and the Cartesian coordinate system allows us to visualize functions in a very, very nice way. So the first thing you got to remember is that f of x is the output of a function f, and x is the input of the function, right? That notation is still critically important. X is the input, f of x is the output, the thing that comes out of the box, right? So what we can do is we can label the inputs of f along the horizontal axis. We'll call it the x-axis because our inputs are x. And we can write y equals f of x to identify the outputs of f, along the vertical axis, which we call the y-axis because we used this letter y. All right, so inputs are labeled along the horizontal axis, outputs are labeled along the vertical axis. All right, hold on one second. Where is it? Okay, maybe that'll help a little bit. Okay, that helps a little bit. All right, so then, yeah, I've said this a bunch of times, but I just have to re-emphasize it. Just remember that f of x is the output of the function. So when we identify y equals f of x, that lets us pass from the realm of abstract functions to the realm of geometry. And that gives us the definition of the graph of a function. So what is the graph of a function? It's the set of all points in the plane R2, where the ordered pair x comma y is equal to the ordered pair x comma f of x, where f of x is the output of the function, right? That's the basic idea. But let me pull up there we go. So one thing that can help us, or one thing that helps us understand functions better when we graph them is this thing called the vertical line test. And you may have seen it before, but it's just a really, really handy test to determine if the graph of something is actually the graph of a function. Here's the start of it. Remember that a function can only have one output for any given input, right? That's one of the properties of a function. So what that means is not every set of points on the plane describes a function of x. I mean, you can draw any picture you want on a plane, right? That doesn't mean that that picture or that graph is going to be the graph of a function. So yeah, not every graph you sketch on the plane can be written in the singular form y equals f of x. We're going to see some examples in just a minute here. So we can visualize the condition that we require of a function by using this very handy test called the vertical line test. So here's the vertical line test. It says this: a set of points in the xy plane is the graph of a function x if and only if every vertical line intersects the graph in at most one point. Or I kind of prefer this interpretation, this equivalent interpretation. In other words, if there's a vertical line that intersects the graph more than once, then the graph does not represent a function of x. So put simply, if you've got a graph on the plane and you draw vertical lines anywhere on that plane, and there's a spot where the vertical line touches the graph more than once, then your graph is not a function. That's pretty much it. Because what that means is, well, I'll say this, the vertical lines are corresponding to inputs that you choose, x values. And then you're basically shooting up those inputs to see where they would touch the graph. And if those inputs touch the graph in more than one point, well, that means you're getting two different outputs for that same input. And that's not a function, right? All right, let's do some examples. We're going to look at these graphs and we're going to see if, oh, actually, I wanted to switch these. I'm going to switch the order of these in a second here. We're going to see if any of them yield y as a function of x, or if any of them yield x as a function of y. This might be a little weird, but we can talk about functions where x is the output and y is the input too. The labels are pretty arbitrary. What's important is the relationship between those labels. So let's start with this one. Let's look at this one right here, y equals x squared. We saw this in the last section, and maybe you can recall what this graph looks like already. If you can, great. If not, no worries. We're going to just do this real quick, label our axes x and y, and we're going to graph y equals x squared. This is the good old parabola. Looks a little bit like that. And the question is y a function of x? So this right here is y equals x squared. That's the set of all points where y equals x squared. Well, let's do the vertical line test. I'm going to get a vertical line going here. There it is. And I'm just going to move this line around on the picture and see if it touches the graph in 2 points ever, right? So look, if I do this, the graph is only intersecting, I'm sorry, the line is only intersecting the graph at a single point, right? Single point, single point, single point, single point. Yeah, so this passes the vertical line test. That means that this thing is a function of x. So y equals x squared does give a function of x. Now, what I want to do is something a little bit different. So let me erase this stuff. Let me erase this stuff. Let's skip down and take a look at this thing right here. X equals y squared. Now, actually, I'm going to move this a little bit too, just to help me out. Uh, this might seem a little bit weird, but one of the things I'm hoping with this class is to get you comfortable with the idea of working horizontally as well. X equals y squared, we can graph that on the xy plane. It's just now the x's are being given as squares of the y's. So this one actually looks like this. And this is the graph of x equals y squared. There it is. So it's basically sideways, right? In fact, if you were to turn your head, wait, I gotta do it this way, turn your head sideways, you would see the typical parabola you're used to. Now, let's see if this graph represents a function of x. So we're gonna do the vertical line test again. Let me get my vertical line. I'm going to move this vertical line around, right, and see if it touches the graph only at one point. It's already breaking, right? This does not pass the vertical line test. If I put the line anywhere here, notice the vertical line is intersecting the graph at 2 points. Yeah, so that means this right here, not a function of x. Not a function of x, as we can see by the vertical line test. Now, what's interesting is we can do something a little bit different. This graph may represent a function of y. We just have to turn our vertical line horizontally and see if that works. So we're going to do that here. Erase this stuff. Oops, too much. No. All right. All right, let's make a horizontal line now. I'm going to do it right here. I'm going to move it around. Now, if I look at this horizontal line, ooh, look, it's only touching the graph at one point at a time, right? Just like that. So what that tells us is that this formula here This is a function of y, meaning x is a function of y. So I could say x is a function of y. There we go. So this is a situation where it's a function one way, but not the other. And that's going to become even more important when we get to inverse functions, which is at the very end of this chapter. All right, now let's do the next graph. Let me erase these, erase all of these, erase this. Let's do y equals x cubed. So we're going to shift over to this one. This is another one of those graphs that you want to have memorized. We're going to look at much better versions of these graphs, computer-drawn versions of these graphs in just a minute. But this is what it looks like. A bit like that. So this is y equals x cubed. Oops, there we go. Y equals x cubed. Same question. Is y a function of x? Is x a function of y? We're going to see right now. So let's start with our vertical line. There we go. And let's move the vertical line around. All right, only touches once, 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 once. Looking good, looking good. So this formula is describing y as a function of x. All right, so maybe I'll write that right here. Right? So this equation is describing y as a function of x. Let's do a horizontal line. Here we go. Oops. And let's move this around. All right, if I move this around, okay, only intersecting once, once, only once, only once. Yeah, yeah, it's only intersecting the graph at a single point at any given time, right? There we go. So that means that this equation is also describing x as a function of y. So we get both in this case. And I should say this, y is a function of x and x is a function of y. There we go. All right, now let's look at the one at the bottom. We saw this graph in a previous section, the last section. This is the graph of the unit circle. We're going to see this one again a couple of times in this section, in the next section, actually. So let's graph this one for a second. Oops, this one. Yep. I'm going to use the computer assistance here. There you go. Thank you. Okay, so this is the unit circle, 1, 1, negative 1, 1. And the question is, does this equation describe y as a function of x? Does it describe x as a function of y? Let's check. Let's do our vertical line first. Oops, that's a little too thick. Here we go. Vertical line. Let's move it around. All right. Okay. Good so far, but then, it's hitting twice. It's hitting that circle in two different points. And as I move this line around, as I change the x values, the y values there's two of them, right? There's two, except for right here at the end and right here at the end. But everywhere else in here, it's hitting twice. Boom, boom. So this failed the vertical line test, meaning this equation does not give y as a function of x. If you put in an x value, you're going to get two y values no matter what. Oh, not no matter what, except for at the endpoints, right? Let's flip things. Let's look at it horizontally instead. Let me do this. I'll just do a new line. Here we go. Now we need a horizontal line. Let's move it around. All right, now, same issue here. Maybe you could kind of tell before I even started. As I move this horizontal line around, it hits the graph at two different points. Hits the graph at two different points. So this equation also does not give x as a function of y, meaning if you put in a y value, like pick any y value you want, maybe this y value here, and you're going to get two different x values, not a function in this case. So here's a situation where this equation is not describing a function of x, nor is it describing a function of y. So you got to think about these things, right? But luckily, this vertical line test and this horizontal line test can help us out with that kind of thing. All right, now let's talk about getting some info from a function. I'm sorry, getting some info about a function from its graph. One of the beautiful things about graphs is you can look at them and get information just by looking at them. So here what I've got is I've got the sine curve, sine of x, plotted on the interval negative 2 pi to 2 pi. We are going to explore this graph in great detail in chapter 6, big time. But we're going to see it a couple of times before then. We're going to see it now, and we're going to see it again in the next section when we look at transformations of graphs. So first question, just by looking at the picture, what is the domain? In fact, you know what? This is a good time for you to try this on your own. So let me throw up the thinker. Look at this and just think about these questions for a minute. Okay. Now say something out loud about what the domain is. Just start with that. Remember, you don't have to say it to anybody. Don't feel weird about it. Just say anything out loud to give your brain that feedback, and then we'll do it together after you give it a try. Start with the domain. Can you tell what the domain is by looking at the picture? Okay, now let me ask you this. What about the range? Can you tell what the range is by looking at the picture? Right. Now let's do it together. So remember, the domain is the set of all the inputs that the function can take. And in this case, we can see that the domain basically starts here and ends here. So the domain in this case is all of these x values that you see right here. So here the domain is going to be negative 2 pi to 2 pi, just like so. Now let's check out the range. Let me erase this. So the range is the set of all the possible outputs. And now what we're doing is we're looking at the y-axis, right? Um, Looking at the y-axis, there's like a maximum here. Let me change the color. There's a highest point that the graph ever reaches, and it's right here at 1. And there's also a lowest point, and the graph never goes below that point, negative 1. But it reaches everything in between. There's no holes in the range or anything. So here the range is going to be negative 1 to 1, inclusive, right? It's including those endpoints including those endpoints. So here we've got a domain of negative 2 pi to 2 pi, inclusive, and a range of negative 1 to 1, inclusive. And we were able to tell this just by looking at the graph. Now, let's look at some points. Race. Oops, actually, I don't want to do that. Keep that. So here, this is a good one to think about too. This one's asking, what is sine of 0? What is sine of 3 halves pi? And what is sine of 3 pi? So let's go through these. The thing I'm going to keep repeating that I want you to remember is this is the output of the function, right? This is the output of the sine function. So we want to know, what is the y value when x is equal to 0? Okay, well, x is equal to 0 right here, and the y value is 0. So sine of 0 equals 0. Or, yeah, right there. Okay, what about sine of 3 halves pi? Let's see. Where is 3 halves pi as an x value? It's right here. There's 3 halves pi. So what is the corresponding y value? Negative 1. So here, sine of 3 halves pi is equal to negative 1. Just like that. The output is negative 1. All right, what about sine of 3 pi? Let's look for it. So we're looking for an input of 3 pi. See, 3 pi is over here. Okay, well, this this function here is not defined at 3 pi, so this one does not exist. Yeah, sine of 3 pi doesn't exist. I'll just write dne. Now, here's one thing I want to mention about this particular graph. It does, or I'll say this, this graph is specifically cut off at negative 2 pi to 2 pi. We could extend this graph as we'll do in chapter 6, but as it's presented in this picture, it's cut off at negative 2 pi to 2 pi. Okay. Ooh, here's a good question. This is a good one. It says, how many times does the line y equals 1 half intersect the graph? Okay, so y equals 1 half, that's going to be a horizontal line because all we're saying is that y is 1 half. Notice x does not appear. That means x can be anything we want. So what I'm going to do, I'm going to draw a horizontal line, a long one. There we go. And I'm going to move it to the output value 1 half. Here we go. Let me place it. Okay, that's 1. Need to go about halfway between 1 and 0. There. Okay. Now, that red line, that horizontal line, is intersecting the graph a bunch of times. Let's just count them and mark them. One, two, three, four, and that's it. So four times. So this is intersecting the graph four times, just like that. In other words, there are there are four inputs that correspond to the output one half. We'll learn more about those in chapter 6 too. All right, how about this one? Okay, this question says, for what values of x does sine of x equal 1? Remember, sine of x is the output. So what this is saying is, for what inputs is the output equal to 1? Okay, this horizontal line is going to come in handy again. So if the output is equal to 1, let's draw a line there. I'm going to do this and move it into position. Okay, here's 1. It's placed at 1. And we just want to know, what are the x values that'll give us that output? Well, I noticed a couple intersection points. Here's 1, and here's 1 right there. And that looks like it. So if we trace this down to the x values, we can see that there are two x values that give us an output of 1. One of them is -3/2 pi. In fact, maybe I'll say x equals, right? X equals, and x equals pi over 2. All right, so those are the two inputs that give us an output of 1. All right, now let's look at the next question here. Next question says, for what values of x is sine of x positive? Ooh, let's think about this for a second. For what values of x is sine of x positive? So this just means, when is the output positive? And the beauty about a graph in this situation is we can see the result by looking at it. Remember, if the output is positive, that means it's going to lie above the x-axis, right? Because the outputs are positive up there. The y values are positive when they're above the x-axis. So what we're really looking for is, where does this graph lie above the x-axis? Okay, I see a bunch of places where that's happening. Maybe I'll sketch it. Yeah, okay, so here, let me do this. Let me do this. It's clearly above here, and it's above here, and then it's actually below the other points. See, here it's below the x-axis, and here it's below the x-axis. So maybe I'll label this a little bit. Here I would say f of x is greater than 0. Down here I'd say f of x is less than 0. Or sorry, sine, I guess sine, but let me erase that here. Sine, sine, there we go. Okay, okay. So there's a lot of x values where it's going to be above the x-axis, right? Can zoom in a bit on this one. Um, One thing I'm worried about though is those endpoints, right? Notice this inequality is strict. Oops. This inequality is strict. So that means we can't be on the x-axis. That means these actual points do not satisfy this inequality. So maybe I should draw like an open circle, kind of like that there, and that there, and then that there, and that there. So it looks like there's two intervals. One thing I want to point out, this function is continuous, right? The curve is unbroken. So our answer is going to be intervals, not points, not individual points. There's infinitely many points where this is true. So what we need is, we need this interval from here to here, and we need this interval from here to here. And on those two intervals, sine of x is positive. So what's this first interval? It's -2 pi to -pi. So I'll write that here. -2 pi to -pi, union 0 to pi, 0 to pi, just like that. All right. Now this last question, let me erase this stuff. This last question is something we haven't talked about yet, but we're going to talk about it a lot in chapter 6. It says, what is its period? So some graphs or some functions actually have what's called a period, and it's basically how long it takes for the graph to repeat itself. So you'll notice here, this is like a wave, like an ocean wave, right? And it repeats. So the length, the length of the interval before it repeats is what's called the period. So maybe here you'll notice, this piece looks the same as this piece. And then here, each one of these pieces is a length of 2 pi in terms of x values, right? This is 0 to 2 pi. This is negative 2 pi to 0. So this is actually a moment where the period is 2 pi. There we go. And we'll talk more about that as the course goes on. All right, so we just got a ton of information from that graph. Let's talk about getting some other information about functions, some information that we're going to study a lot again later on. Want to build all this stuff up. We need to talk about the zero of a function or the root of an equation here. So given a function f, if there is an input r such that f of r equals 0, the output is 0, then that number r is called a zero of f, or we can call it a root of the equation f of x equals 0. Those two terms are interchangeable in that sense. This example is a good one, right? So this function, x squared minus 4, it has two zeros, one of them at -2, one of them at 2, because if you plug those numbers into the function, you get out 0. So f of -2 is -2 squared, which is 4. 4 minus 4 is 0. So -2 is a zero of the function. 2, if I plug in 2 here, I get 2 squared, which is 4. 4 minus 4 is 0. Boom. So these are what we call zeros of the function, or sometimes just roots of the function. Now, why do we care about this? This is an important idea. This is one of the most fundamental mathematical problems, and for many of you, you're going to use it a lot in your careers and in your STEM courses. So for a lot of scientific analysis, a lot of the problems that you work on can be converted into what we call a root finding problem. Basically, you want to find the zeros of a function, or you want to find the roots of an equation. And if you can convert your problem into that, we have a ton of methods to help you at that point. So what we do is we construct a function of interest, and we want to find the zeros of that function because the zeros correspond to some data set of interest. You're going to see this explicitly in this class, but really explicitly when you get to Calc 1. So in Calc 1, you can actually use this root finding method to find the maximum and minimum values of a function. And remember what we were talking about in the previous section about finding the range of a function? That can be hard, but when you have calculus, you can compute the derivative of a function, set it equal to 0, and find the zeros of the derivative. And that can help you determine what the range is. Cool stuff. So this is what we're building you up for. You're going to see this in the next class, next semester when you take Calc 1, all right? So think about these ideas. Root finding problems, finding the zeros of functions. Let's do it right now. We're going to do this in two parts, and you're going to try this on your own first. We're going to find the domain and the zeros of this function given here, right? So first, think about it for a sec. All right, now say something about what you would do first. Maybe tell yourself how you'll find the domain, right? And now try to work it out on your own, and we'll do it together. Find the domain and the zeros. Okay, let's do it. Um, Okay, so let's remember what the domain is, right? The domain is the set of all the inputs that work. And what we had talked about in the previous section is finding the domain. Well, you can either find everything that works, or you can look for the problem points, the points that'll break the function and take those out of the domain. So here, the one thing I'm concerned about is we've got a rational function, so we got to watch out for division by 0. If we plug in a t-value, that results in a division by 0, we've got a problem. So in order to find the domain, we need to cut out the points that'll make the denominator 0. More specifically, we're going to need this. We need t plus 2 to not be 0. So that means we need t to not be -2, right? If we plug in -2, we're going to be dividing by 0, we got a problem. So I think that might be it, though. I don't see any other numbers that are going to cause problems. So the domain is everything except -2. Here we go. So Same process that we just did a second ago. We set the denominator equal to 0, found where it was equal to 0, and now we are cutting those numbers out. So the domain of G is all real numbers, t, such that t is not equal to -2. This is that set written in set builder notation. This is that set written in interval notation. And like I said before, you'll get lots of practice with this on the homework. Remember, the interval here is everything from, well, everything between -infinity and -2, skipping -2, and then everything between -2 and +infinity. Here we go. Maybe I'll draw a quick picture of it. Here. Here's the real line, x. Here is the point, -2. What is the domain? Well, we're skipping -2. We're going that way, and we're going that way. That's what it looks like visually. Right. So we found the domain. Now let's find the zeros. And the thing that I want you to remember about finding the zeros is this very, very basic setup. When you want to find the zeros of a function, you set the output equal to 0, and then you solve for the inputs. So we're going to set the output equal to 0 and then solve for t. Here we go. Output equals 0. Well, what is the output equal to? T plus 1 over t plus 2. So we need to solve, we need to solve this equation for t and just find where this is true. We can multiply both sides by t plus 2. We get a cancellation. Now we're left with this, t plus 1 equals 0. So that means t is equal to -1. That means -1 is the zero of this function, and there's only one of them. Let's check. Let's take -1 and plug it back into the function. Here we go. -1, -1. Okay, -1 plus 1 is 0. -1 plus 2 is 1. 0 divided by 1 is 0. We're good. That is the zero of the function. In this case, there's only one of them. Geometrically speaking, remember we were talking about this in the previous chapter. Geometrically, what that means is the graph of this function crosses the x-axis at -1. There you go. All right. So what's next here? We talked about the zeros of a function. Now we got to talk about the graphs of some important functions. I'm going to pull up Desmos so we can see what they look like. I am not a big fan of memorization. You will very rarely hear me say you need to memorize this. In my experience, you really don't need to memorize a lot when you're doing meaningful mathematics. There's some things you do have to memorize, though. And this is one of those situations where there are several graphs that you must have memorized. Like you really just can't avoid it. You have to have these memorized, all right? Um, let's see. Oh yeah, yeah. And the reason is because these structures appear throughout the course in calculus and beyond. One of the things that I will specifically ask you to do on the exam is just give a, oh, 1 second. What is this? Hold on, hold on. Got a little red flag here. One moment. Okay, maybe I can do this. Hopefully that helps a little bit. Okay, let's take a look at Desmos. I got it pulled up right here. Oop, not that, not Mathematica, Chrome. All right, so you can follow that link on the slides. And what I've got is I've got a list of all of the important graphs that you need to memorize, all right? Not as hard to commit to memory as you might think. Some of these you've probably seen a bunch of times before, but let's go through them together. First is the graph of a constant function. F of x equals b. This just means the output is a single number, whatever that number b is. So this is what's called a constant function. Constant functions are just horizontal lines that intersect the y-axis at whatever that value of b is. Okay? So make sure you recognize this. F of x equals b means a horizontal line crossing the y-axis at whatever that value is. Next, one of everyone's favorites, good old f of x equals x. This is the diagonal line. This has the formula x. We actually call this the identity function. This is the identity function because you put x in and the output is just x again. So this is like the function that doesn't really do anything. It just spits out the thing that you put into it. So if x is 2, the output is 2. If x is 4, the output is 4. Same thing. All right, everybody's next favorite, x squared. This good old parabola, we're going to see it a lot. This is taking the inputs and it is squaring them. So if we take 0 and we square 0, we get 0. Let me zoom in a bit. If we take 1 and we square 1, we get 1. It starts to get more interesting when we get away from 1 in either direction, I'll say. If I put in 2 and I square it, 2 squared is 4 right here. Let me move right to that point. Come on, there it is. 2 squared is 4. Let's look at some negative values. Negative 1 squared is 1. Negative 2 squared is 4. Come here. There it is. Negative 2 squared is 4, right? Remember, because a negative times a negative gives you a positive. So negative 2 times negative 2 is positive 4. So this is a graph you want to have memorized. This is the graph of x squared. We're going to see it a lot, and we're going to use it a lot when we get into more complicated functions. All right, now let's look at x cubed. This is another important function, x cubed. It looks kind of like this little swoosh, this little like wave, right? Just like so. This is taking the input and multiplying it by itself 3 times. So here, 1 times 1 times 1 is 1. But it grows a bit faster than x squared, right? So what if I plug in 2? Well, 2 times 2 times 2 is 8. So it's growing a little bit faster, right? There we go. 2 times 2 times 2 is 8. So if I plug in 2, I get 8. Now, one thing to notice here that makes this different from x squared is that if I plug in a negative number, I get a negative output, right? Here, if I plug in negative 2, I get negative 8. Negative 8. And that makes sense if you think about it. You break it down, right? Negative 2 times negative 2 times negative 2. Well, that's a negative times a negative times a negative. So it's going to be negative. And 2 times 2 times 2, that's 4 times 2, which is 8. So we're getting negative 8. And this is what x cubed looks like. We're going to see this one a lot as well. Okay, now we're going to look at the inverses of these two functions. So this is a little flash forward to what we'll talk about later. This is x squared, and if we cut off, if we cut this off so we just have the positive part, I should say for positive x values, just take this right piece right here, then we get the square root of x. There it is, square root of x. This is very much like, kind of like the graph of x equals y squared that we saw, but it's just the top part, right? So here, this is the square root function, and we're going to see this one a lot. We saw it briefly in the previous section when we were talking about the domain and the range of a function. This is what it looks like, square root of x, just like that. Another one you want to have memorized. Now let's take a look at the cube root of x. This is the cube root of x. And again, it's very much related to x cubed because it's actually the inverse of x cubed. Inverse of x cubed. So it's like that one. Here's x cubed. Here's x cubed. Here's cube root of x. X cubed, cube root of x. And we're going to talk about this in the future at the end of this chapter, but the way that we're getting the graph of cube root of x is we're actually reflecting it across this one, the diagonal line. We're reflecting it off of we are reflecting it around the graph of the identity function. There we go. It's symmetric. So you want to know that one too. Now let's look at 1 over x. 1 over x. So this is what 1 over x looks like. This one we actually explored way back in section 1.1. We were just looking at the positive branch of it right here. The positive branch right here. So if you take if you take 1 and you divide it by x, this is what you get. Now, if x is negative, you're going to get a negative result, just like that. Notice that there is what we call an asymptote at 0. There's a vertical asymptote here at 0 because you can't divide by 0. Can't divide by 0, all right? So can't divide by 0. 0 is not in the domain of this function. And this is what 1 over x looks like. Now let's take a look at 1 over x squared. So 1 over x squared is similar. You still have this kind of eccentric swooping behavior, right? But remember, when you square something, you always get a positive number. So that's why over here, when I plug in the negative values for x, I'm still getting something above the x-axis. I'm getting positives, right? I'm getting positive y values, positive outputs. There we go. Still an asymptote when x equals 0 because you can't divide by 0. So that's still there. All right. Okay. Next is the absolute value function. We're going to see this one a lot. You'll see it a lot more in Calc 1. The absolute value function looks like a v. It is very similar to the identity function f of x equals x. Except remember, so like here, f of x equals x. When x is positive, absolute value just spits out the number again, right? That's what we talked about in chapter 1. Now, if the x value is negative, the absolute value function takes the opposite of that number to make it positive. So it's literally taking this red line and basically reflecting it across the x-axis, taking all of these negative outputs and making them positive. So absolute value of x looks like this v right here. That's the big idea, all right? Okay, now let's talk about circles a little bit. We've got a whole section dedicated to circles in chapter 6, so I won't dwell on them too long. But it's good to kind of recognize them starting now. You're really going to want to recognize them a lot when you get into calculus and beyond. So a circle centered at 0, 0 with radius r has this equation, and there it is. There it is. So what I've got here is the unit circle, the circle of radius 1. And we've seen that a couple of times now already. But this equation can be generalized. R can be any positive number you want to pick for a radius, right? It could be 2, 3, e, pi, anything in between. So there we go. I'm actually going to keep these positive just to keep intuition. We don't need to worry about negative radii. Doesn't make sense in this context, but as r gets larger, the circle gets larger. There it is. So this is the equation of a circle centered at the origin with radius r. Make sure you've got it memorized. Now, the other thing we talked about earlier in this section was this graph does not represent a function of x, nor does it represent a function of y, right? Well, the reason for that is we got those double intersections, right? Here, let me tweak this a minute so we can take a look at this. Let me do this. Let's say x equals, oh, geez, I don't know. M. Oh, nope, nope. Let's say x equals 2. But I wanted to move it. So maybe x equals c. Am I allowed to use c? Did I already use these letters? Well, I was hoping to move this line around. What am I? X equals z. Hold on. T. No, I want to let me. Well, ah, I'll just use b in this case. X equals b. That way I can move it around. All right. So remember here, as I move this line back and forth, it hits the graph at 2 different points, right here and right here. Yeah, so as I move that, as I move that horizontal line, it's intersecting the graph at 2 points. So this graph does not give y as a function of x, right? It's not a function of x. So the reason for that is because we're getting those 2 outputs. But one way we can get around that is we can pick the top half of the graph and the bottom half of the graph and view them separately. And that is exactly what this is. So this formula right here. This is the formula for the top semicircle, the upper half of the semicircle of radius r. I can change r, right? But now, as that vertical line moves around, it only intersects the graph at 1 point. So now we do have a function of x. We can plug x into this formula and get out a single y value. So this is a function that describes the top half of the semicircle. The way that we got it, we'll explore this more later, is we just solved this formula for y. But you'll see in the activity, when you solve this formula for y, you're going to get 2 results. You're going to get this positive result that you see right here, and you're going to get this negative result, the bottom semicircle. Here it is. Notice the relationship here, negative this thing. So this is the top. There you go. That's the top, and that's the bottom. So r squared minus x squared, you take the square root. Okay, last two, we could instead solve this equation for x. And when we solve this equation for x, what we get is this. We get the right semicircle, or we get the left semicircle right there. So left, right. Oops, there you go. Left, right. Same idea. So basically what we're saying is if we restrict things just right, we can get functions of these variables. But as it's given right here, formula for a circle doesn't give a function of x nor a function of y. But we can find the functions for the top, the bottom, and the left and the right. All right. So this list right here, these are all the important graphs that you need to memorize. And I'll be honest, on the test, I will ask you to just give a rough sketch of every single one of these. That's it. It'll just be a big page where I'll say, give a rough sketch of x squared, give a rough sketch of x cubed. So these are ones you do have to memorize, commit them to memory. We're going to see them a lot. All right. Okay. Now, moving along, the next thing we got to talk about are piecewise functions. So what happens a lot of times is a function will use a different set of rules for different sets of inputs. That's what this is. So what that means is the way the function works will change depending on what the inputs are, what you put into it, right? So for example, we may want our function to triple the input when x is between negative infinity and 1, maybe just like triple everything, right? But then we might want it to square the input otherwise. And that gives us a piecewise function or a piecewise defined function. So let me go through the pieces here. This is the structure of a piecewise function. You have the rule for the formula here. I'm sorry. You have the formula for the function here, and this is the condition placed on the inputs. Here's the other formula for the function, and this is the condition placed on the inputs. So what I'm saying here is, hey, whatever x value you put in, do this if x is less than 1. Or do this if x is greater than or equal to 1. And this is what the graph looks like. That's what the graph looks like. So right here, this is the rule 3 times x. But it's only applicable when x is less than 1. When x is less than 1. Then once you actually get to the number 1 and beyond, you're going to square it. So that's why it looks kind of like that parabola, like piece of a parabola right there. So here the rule is changing at a certain point. In this case, it's changing when x equals 1. And that's why I kind of color coded things here. So when x is when x is less than 1, this is what the graph looks like. When x is greater than or equal to 1, this is what the graph looks like. Just like so. Um, uh, yeah, basically the idea is this. If you've got piecewise functions, the graphs look like they normally would, but the conditions given over here, they provide like a window, like a restriction window, where only the part of the graph in the window can be seen. So it's kind of like, if you wanted to if you wanted to graph this, just graph the line 3x, but then only show the line on the red window. Like that. Okay, then graph x squared like you normally would, right? But then only show x squared on the blue window, like that. That's how piecewise functions work. Um, Absolute value is kind of the same way. So this is the graph of x, that's this one, but only on the blue window. And then it's the graph of negative x, but only on the red window. So you can describe the absolute value function as a piecewise function, just like we saw back in section 1.4. I think it was 1.4. Yeah. And that's the idea. So piecewise functions are very flexible. The other thing is they don't need to be defined on all of the real numbers. Piecewise functions can have holes in them. They can have cutout intervals. There can be any number of rules. You could have a dozen of these rules. You could have a trillion of these rules, however many you need. You're just saying what to do on certain intervals or at certain points. So here's one where I actually have 3 different rules depending on the input t. Right? So here, g of t, the rule is going to be 1 when t is less than negative 3. Remember, this is just a constant function. G of t equals 1. right? G of t equals 1, but only when t is less than -3. So that's why you're getting everything this direction. Now, looking at these conditions, notice that this is not even defined between -3 and 0, so nothing is going on with the function here. The function's not defined there. If you tried to take a number in this interval and plug it into that function, it wouldn't give you an output. It's not defined there, doesn't exist. Okay, but when you get to 0, that's when you're going to start squaring the input. So between 0 and 1 inclusive, you square it. So this little piece, maybe I'll do it right here. This little piece, g of t is equal to t squared. And it looks like the parabola again, right? It looks like the good old parabola, like that, but only on that blue window, only on this window right here. That's the only place you're seeing the parabola. Okay, now, whole different rule when t is greater than 1 or less than or equal to 2. This is another line. This is a line with slope 1/3 and y-intercept 1. We'll have a whole section on these when we get to chapter 3, but this is what the line looks like. See if I can kind of sketch it like that. That's what the line looks like, but we're only looking at it on this window, and you get this. That's the idea. So let me just finish my little sketch here. We need a little more space. There you go. This is g of t equals 1/3 t plus 1. All right. Yep. Okay. So that's how piecewise functions work. We're going to practice those in the activity. The next thing we got to talk about is combining functions. So a lot of times what we want to do is we want to take two different rules and we want to combine them in a simple way, like addition, subtraction, division, multiplication. So the way that we define these combinations is pointwise. Pointwise. We basically say what to do at any given point. So in other words, if you're given two functions f and g, we define the sum function, as the sum of their outputs. So this is a little bit weird. Let me explain this notation. So the function we are looking at is the function f plus g. So what does that function f plus g do to the inputs? Well, it takes the output of f and adds it to the output of g. Which makes sense, right? That's a natural way of defining these things. This little fancy symbol here, this colon equal sign, that actually means to define. So we are defining this function as this rule right here. So there's nothing, there's no like algebra going on here. We're not like distributing anything or anything like that. This is just a definition. The function f plus g of x is f of x plus g of x by definition. All right. Nothing fancy, just by definition. And you might be able to imagine what happens if we do other things to these functions. If we subtract, if we multiply, if we divide, we're just going to take their outputs and do that operation to the outputs. So here's the rest. What is the function f minus g of x? Well, we take the output of f and subtract the output of g. What's the function fg of x? We take the output of f and the output of g and we multiply them. What is f over g of x? We take the output of f and divide it by the output of g. And that's it. That's how we combine functions. So let's try it for a second. Let's say f of x equals x squared and g of x equals 3x plus 4. And what I want you to try is to compute these. I want you to try to compute f plus g of x. Start with that. And then maybe do f times g of x, okay? So think about this one on your own for just a moment. Right? Now, say something out loud about what you could do. How would you start this? Right? And now try to work those two out, and then we're actually going to do all four in just a minute here. Right, here we go. Okay, I'm going to flip to the next slide because we have all the solutions there. So, walking through it carefully, f plus g of x is adding the outputs, but the output of f is x squared, and the output of g is 3x plus 4. So this is what f plus g of x looks like. not too bad. There's no simplification we can do. We're just done at that point. It stopped. Okay, what about f minus g of x? Well, now we're going to take the output of f and we're going to subtract the output of g. Want to be a little bit careful here though, because we're subtracting the entire output of g. So we're going to need some parentheses here. We're going to subtract the entire output of g. So you got to be careful. Parentheses are necessary here because that negative sign is going to distribute to both of those terms, and we get this instead. Right, no more simplification can be done. That's about it. Now let's multiply. Fg of x is output of f times output of g. Output of f times output of g. I could distribute x squared to 3x, x squared to 4, and I get this. That's it. What about f over g? Well, f divided by g of x is the output of f divided by the output of g. There's the output of f. There's the output of g. And you may be able to do more if you want, or you can leave it like that. You could actually divide those using the division algorithm if you wanted, which we'll talk about in chapter 3. Okay, so one thing I want to point out here is we are combining these functions, but remember, functions cannot exist without a domain. So we need to consider the domain of these functions even before we start trying to combine them, right? So to talk about how we're going to describe these domains, we need to go back to a little bit of set theory, and we need to talk about the intersection of sets. All right? So intersection of sets, kind of a flashback to what we did the previous section. But let A and B be sets, then the intersection of A and B is the set of all elements that are contained in both A and B. So here, if we look at the Venn diagram, so maybe I'll do, here's A and here's B, then this little space on the inside here, that is the intersection. This is the intersection of A and B, like so, just like so. So the important thing here is that whatever is in the intersection, it's got to be in both of the sets, not just one of them. It's got to be in both of them. We denote the intersection with this little upside down U, a little N, if you want to say it like that. And it's literally just the set of all elements in A and B. Okay. Let's do a practice problem, and I want you to try this one on your own. See if you can find the intersection of these two sets. We saw these two sets in the last section too. Try to find the intersection. Think about it for a sec. Say something out loud. Maybe what's something that you know is in both of those two sets. And now work it out. Try to write the intersection in interval notation. Write the interval that gives the intersection of these two sets. Right. Okay, now let's work on it together. Let's see. Here's the full calculation. Like I said in the last section, you don't need to write out this full calculation. If you can do it intuitively, great. If you want to write it out, great. Whichever you want to do. But here we've got negative infinity to 16. Here we've got 0 to 87. We need to find where these things overlap. Like where do they overlap? Where are they connected? Um, let's see. So x has to be less than 16, but it's got to be greater than or equal to 0 and less than 87. So that means it's got to be greater than or equal to 0, but less than 16, just like so. So this is the intersection right here. This is one where I really like the picture. So let's take a look at the picture now. The picture here, this is the interval negative infinity to 16, excluding 16. This is the interval 0 to 87, including 0, excluding 87. And what we're looking for is the overlap. We're literally looking for where these two sets overlap. And there's a little bit of an overlap here. The overlap is right here from 0 to 16, including 0, excluding 16. That is the intersection of those two sets. That's the idea. Now, why is this important? Why do we need to talk about intersections? Why do you care about this? Why are we even talking about it? Well, if we want to combine functions, they only make sense on the intersections of the domains of those original functions. So let f and g be functions. where we have the domain of f and the domain of g, then if we want to talk about the function f plus g, it only makes sense on the intersection of their two domains. And this is true for all of these combinations. F minus g is only defined on the domain of f intersected with the domain of g, only defined where those two domains overlap. Same for f times g, same for f divided by g, but there's an extra stipulation. Can't divide by zero. So what is the domain of f over g? It's the intersection of the two domains, but you also have to cut out all the points where g of x is equal to zero. Got to be careful there, right? And that's how we do it. So consider these intersections before you start combining functions. And you're going to see why right here. So here I've got a really nice visualization of this. Here I've got the function f. Where is it? And yeah. So this is the function f. This is the function g. And if we wanted to add those two things, if we wanted to add those two functions, the only place that makes sense is over their intersection. The only place that makes sense is over their intersection. Okay. Yes, yes, yes. Yeah. So where is their intersection? Well, just like I showed before, here's the domain of f, here's the domain of g, here's the overlap. So we can only talk about combining these two functions over this purple interval right here, this purple region. All right, let's try it. Yes, yes, yes. Okay, I want you to try this one too. Try this one on your own. So here's two functions. F of t equals 2 over t minus 1. G of t equals t over t plus 4. And I want you to find the domain of the sum, f plus g. All right? Think about it for a minute. Finding the domain. Right. Say something out loud. What are you going to do to find the domain of that combination, that sum? Right. Now try to work it out. Think about intersections. Think about the domains of the two functions and try to find the intersection of those two domains. Right. Now let's do it together. Um, Looking at it, I can see this already. So the domain of f is going to be all the t's in the real numbers as long as t is not equal to 1, right? Oops. There we go. Because if t is equal to 1, then we're dividing by 0. The domain of g is going to be all of the t's such that t cannot be -4. Yeah, because if t is -4, g is going to have a problem. G is going to have a problem. So now we just need to find the intersection of those two sets. So the domain of f plus g is going to be the domain of f intersected with the domain of g. And that's just going to be, well, the set of all t's such that t is not equal to 1 and t is not equal to -4. There we go. Yep, that's it. Let's check. Boom, that's it. All right, intersections. Now, finishing off here, one of the things that's really handy is looking at these kinds of graphs. What would the graph of the sum look like? Like if you had these two pictures, there's no formula given, right? What would the graph look like if you added these two graphs together? And that's where we start talking about what's called graphical arithmetic. We can use the graphs of these functions to make sense of and build intuition for the graphs of these combinations. And all we're really going to do is we're going to rely on the fundamental intuition that we talked about in chapter 1, the meaning of addition, the meaning of subtraction, the meaning of multiplication, the meaning of division, right? What you can do is you can literally take these graphs and do those operations to them, and that will give you the picture of the resulting graph, right? So one thing you want to remember is we're setting the outputs equal to y, right? So the outputs here are equal to y. All the outputs are plotted on the y-axis. So what that means is that the value, the output f of a, at any x value a, gives the length of a line segment extending from the x-axis up to the graph, just like that. So the height of this line segment is literally the output value of the function. Very, very literally. If the line is going down instead, then it'll be assigned length. It'll be negative instead, but the distance will be the same. The absolute value will be the same, right? So here, this is the height f of a. Now here, this is the height g of a, right? So we're at the same point A, right? A is in the domain of both of those functions. At this same point A, we're taking the height of the graph of G and the height of the graph of F. And if we want to add them, if we want to add these two functions, we're just going to add these two lengths. Here's the height F of A, here's the height G of A, and this total height is the value of F plus G of A. And this is what's called graphical addition. This is how you do it. You go through every single point in the intersection of those two domains, and you just find these line segments and you operate on them. You add them together, you subtract them, kind of like we were doing with the Cuisenaire rods or the strip diagrams back in chapter 1, right? Section 1.1 even. That's really all that's happening when you add these two graphs. Take the height of F and the height of G and stack them, and that gives you the height of the combination. And then you do that for every single point. And when you do that, you get this. You do that and you get that. So literally, it might look kind of weird, but this graph plus this graph is equal to this graph. But remember, the graph is only defined, this combination is only defined on the intersection of their two domains, which we saw right up here. So there you go. If you take this height and you take this height and you add them up, you're going to get something that's like up here, right? Some point up here. And that's what you're seeing right here. And that's the idea. That's how it works. That's really how it works. So when you think of these outputs, f of a, f of whatever, literally they are heights. They are heights. So more generally, you can do this with any of those operations: subtraction, multiplication, division. This is called graphical arithmetic. You can try the others with these pictures if you want. If you've got a tablet right now, you can literally draw the line segments and put them together and see what you get. All right. All right. On that note, it's time to play. So I'm excited to do these activities with you. This stuff can help make a ton of sense of all the things we're talking about. Um, uh, yeah, you'll see. Once you can do the graphical arithmetic and you can make sense of it, it just clears everything up. All right. All right. I'll stop rambling there. Thank you all again for watching and listening, and I will see you next time.